All right, there's one more way that we find the empirical formula, and that's when we're given the percent composition of a substance. And so example 8.6 is a problem we're going to walk through to make sure that we understand how to do that. They tell us that a substance is found to be 40% calcium, and 12% carbon, and then finally 48% oxygen. All right. Now, here's the first thing that we need to understand about these percentages that are given. These percentages are not values in moles. This is the percentage based on the mass of the compound. Okay, so that's why we're going to take the first step that we're going to take. All right, the easiest way to do this, obviously, if they're giving us the percentage of everything that's in the compound, all of these percentages should add up to 100%, right? And so what we're going to do is we're going to assume that we have 100 grams of this substance. And so if that's true, if that's the mass of the amount of this substance that we have, then it would mean that we have not 40%, but we have 40 grams of calcium, 12 grams of carbon, and 48 grams of oxygen. So we're going to change the percent signs to grams, all right? And we're going to determine what the empirical formula would be if this was how much as far as each substance goes, how many grams of each substance that we have, right? And now we were just working a problem like we were working before. So we have to know what the molar mass is of calcium, and that will allow us to take this 40 grams of calcium and convert it, I'll draw that line a little better, convert it to moles. And we know from looking at the periodic table that 1 mole of calcium is going to have a molar mass of 40.08 grams. And so that's going to give us 0.998 moles of calcium. All right. Now, as far as carbon's concerned, periodic table says that we have 12.0 as the molar mass of carbon. So we do the same calculation again. We would get that we have 0.999 moles of carbon. So again, we're doing the same type of calculation we did here, except we would be using the molar mass of carbon, which is 12.01, instead of the molar mass of calcium like in that one. And then doing the same thing for the oxygen down here, dividing the 48 grams by 16 grams, since that's the molar mass of oxygen, we get 3.00 moles of oxygen. So now we're going to do exactly what we did before, right? We're going to get two ratios. We're going to put the smallest number on the bottom of each ratio. And since calcium has the smallest number of moles, then we're going to do the ratio of carbon to calcium. And we're going to see that that's equal to 0.999 moles of carbon divided by 0.9998 moles of calcium to give us a ratio of 1. In other words, there's a 1-to-1 relationship between carbon and calcium. Again, we can write this with 1 on top and 1 on the bottom, right? And that's 1C. So for every 1C, there is 1 Ca. All right, 1-to-1. And then for the ratio of oxygen to calcium, we have 3.00 moles of oxygen over 0.998 moles of calcium, and that equals 3 oxygen to every 1 calcium is our ratio, 3-to-1, right? And so we write that out as Ca for every 1 Ca. Let's do the Ca first, since that's the one that we've got 1 of. For every 1 Ca, there is 1 C, and for every 1 Ca, there are 3 O's. So that would be our empirical formula for this compound. Now let's do the same exact problem, which is what 8.7 does, but in reverse, okay? So for this one, we are given the empirical formula, Na2SO4. Na2SO4. And so we're going to just work in reverse by saying that we're first going to look at the molar mass of this substance here. So Na2SO4, looking at the periodic table, we get 2, since we have 2 NAs, that's going to be 2 times 22.99 AMU. That's plus the molar mass of sulfur, which is 32.06, or the atomic mass if we're talking about AMU, 32.06 AMU. And then finally 4 times 16 for the oxygen. And so that's going to give us a total atomic mass of 142.04, right, AMU. So in other words, if we have 1 mole of, actually, we don't even need to do that, because remember, we don't have to worry about moles for this one, because remember our percentages, this problem gives us the empirical formula and asks us what's the percentage of each substance that's in here, right? And I said the percentages are based on the mass. Well, we used grams for our mass in the last problem, but we could use atomic mass units in this problem. And so let's just take the total mass, which is 49.04, and we will divide 49.04 into each of the individual masses of the substances that are in it. So for Na, for example, we have 2 times 22.99, right, divided by the total mass in AMU, which is 142.04. And then we're going to take that value, we're going to multiply it times 100%. So that's going to give us a value of 32.3%. That's how much Na is in this compound. For S, we're going to write down the atomic mass, 32.06, divided by the total atomic mass of the molecule. Multiply that times 100%, and we get a value of 22.57%. And then finally, for the oxygen, we have 4 times 16 divided by the total, 142.04, times 100%, and that gives us a value of 45.06%. Now, we just do real quick, we do a rough calculation in our head to make sure that all of these add up to 100%. If they don't all add up to 100%, we did something wrong, right? But 45 plus 22.5, what is that? That's 67.5%, and then add 32.3, that's pretty close to 100%. So as long as we get a number that's close to 100%, we probably did the calculation right. All right, not too bad.